All right, let's talk about something that's happening right now inside basically every piece of tech you own. It's this hidden process called silicon decay, the secret way your electronics are actually aging.
You know the feeling, right? That phone that used to be your pride and joy, the one that felt impossibly fast, and now it just kind of chugs along. You've probably blamed software updates. Maybe you've even thought, hey, are they slowing it down on purpose? But what if the real reason is something physical, something happening deep inside the hardware itself? Well, it's not a conspiracy theory. The real culprit is something called semiconductor aging. And it's not some kind of bug or a flaw, it's a fundamental feature of physics. It's the natural, totally unavoidable process of our gadgets just getting older. So what in the world is actually going on in there?
Let's dive into what we could call your tech's midlife crisis. We're going to find out what's really happening inside these incredibly complex little machines.
So what is semiconductor aging? Well, the key word here is gradual. This isn't your phone just suddenly breaking one day. No, it's a slow, creeping decline in performance and reliability. And it's caused by all these tiny physical, chemical, and electrical changes that are happening constantly over a long period of time.
Honestly, the easiest way to wrap your head around it is to just think of it as microscopic wear and tear. I mean, just like any engine or tool that you use a lot, the parts inside your devices, they get tired. They wear down from all that constant hard work, just on a scale so ridiculously small you could never, ever see it.
Okay, so that raises a pretty big question. Where does all this invisible wear and tear actually come from? Well, it all boils down to one thing: the unbelievable amount of stress our electronics are under every single second they're turned on. And when I say stress, I mean it. Try to imagine this. Inside one single processor, you have billions with a B of tiny switches called transistors, and they're flicking on and off every single second. All that activity creates these intense electrical fields, it generates a ton of heat, and it even causes tiny little physical strains on the silicon itself. It is a non-stop, high-pressure war zone in there. Now, all this constant stress gives rise to a few specific troublemakers. You can almost think of them as the microscopic villains of our story, the ones responsible for all this decay. Let's meet these agents of silicon decay.
So, first up on the villain roster, we've got electromigration. This one is wild. The constant river of electrons flowing through the chip's tiny copper wires literally acts like a water current. And over time, that current physically pushes the metal atoms out of place, slowly eroding the connections from the inside, just like a river carving away at its bank.
Next, we have something called hot carrier degradation. Now, if electromigration is like slow erosion, this is more like a firing squad. In this case, some electrons get supercharged with so much energy that they start acting like tiny microscopic bullets, physically slamming into the transistors and damaging their structure. Every little impact makes that transistor just a little bit worse at doing its job.
And our third main bad guy is bias temperature instability. Think of this one as a tag team villain. You have constant electricity, that's the bias, and you have constant heat, that's the temperature. When you put those two together for a long time, they make the transistors unstable. Their performance gets flaky and unpredictable, which, as you can imagine, is the last thing you want inside a precision computer chip. So let's connect the dots here, because these stresses lead to very real-world consequences. All that heat and those electrical fields, that leads directly to slower performance. You feel that. All that atomic movement, like the atoms getting pushed around, that can make the chip less efficient, so it starts eating up more power. And just general exposure to the environment over time can cause more random errors. It all adds up to a device that just doesn't feel as good as it used to. But it's not all doom and gloom, I promise, because for every one of these microscopic villains, there's a hero. And in our story, the heroes are the engineers who have come up with some absolutely brilliant ways to fight back against this decay. And they have a really impressive toolkit at their disposal. They'll use stronger materials and special coatings to make the chips more durable. They'll actually design redundant pathways, so if one microscopic road gets a pothole, the electrical traffic can just be rerouted. It's genius. They also build in special software that can correct errors on the fly. And of course, things like advanced cooling systems and smart power management are absolutely crucial to lowering that stress in the first place.
So all of this really brings us to the bigger picture here. What we're really looking at is a chip's race against time. This invisible battle, happening on a scale we can't even comprehend, is genuinely one of the most important challenges in all of modern technology.
I think this quote just captures it perfectly. It's not about a sudden breakdown. It's about a gradual decline.
It's a constant, never-ending battle that engineers are fighting against the fundamental laws of physics themselves.
And that is why this whole thing matters so much to you and me. Every single time you use your phone, your laptop, your car, you are benefiting from their success in this fight. It's this deep, deep understanding of silicon decay that allows us to have devices that we can actually count on for years.
So, I'll leave you with this final thought. With every new generation of technology, we're cramming more and more power into even smaller spaces, and that just ramps up the stress and makes the whole aging process happen even faster. The battle actually gets harder every single year. So the big question for the future is, in this race against time, how do we keep winning a battle that, by its very nature, can never truly be won?